Welcome back. Now it's time we look at the characteristics of some amorphous materials. I've mentioned two of these already, and they're based around the glass transition temperature. The glass transition temperature is the point at which there's a discontinuity in the formation line. Above the glass transition temperature the material is rubbery, and below the glass transition temperature the material is brittle. And as I mentioned earlier, that really relates to how those molecules are able to move. Above the glass transition temperature, the material is said to be in structural equilibrium. That means if there is a change in temperature, there is a concomitant change in structure. And below the glass transition temperature, the material is said to be brittle and not in structural equilibrium. So that means if there's a change in temperature, the molecules don't change their structure. On the screen is the same graph we looked at earlier, showing the formation of an amorphous material. The glass transition temperature is the discontinuity. There are two arrows on this graph that we didn't talk about earlier. They're marked 1 and 2. And now it's time that we do need to talk about them. I said that the glass transition temperature is characterized by viscosity. Above the glass transition temperature, the molecules are relatively free to move, and below the glass transition temperature, they're effectively stuck in place. But I never said for how long are those molecules effectively stuck in place. The answer depends on the material, but the smaller the molecular weight of the compound, the more likely it is that the molecules are going to be able to move with time. When we hold a material at a constant temperature, it's called annealing. So what this graph is showing you is what happens to an amorphous material when it's annealed. If you look at the x-axis, annealing is shown as TA. What it means is we're holding the amorphous material at a particular temperature below its glass transition temperature. So that's represented by the arrow with the number 1 next to it. When an amorphous material is freshly made, the molecules are as randomly structured as possible. That means a fresh amorphous material will have the highest energy or highest volume, and so that is represented by the solid line on the graph. If we leave an amorphous material at a constant temperature, even though it's below its glass transition temperature, ultimately the molecules are going to start to move. It's a high viscosity liquid, but it's still a liquid, and the molecules are going to be able to move. It may just be that the molecules take days, weeks, months, or even years to move. And so the changes in an amorphous material may not be apparent when you look at them over a short time frame, but when you leave an amorphous material for a long time, it starts to change. So what I want you to recognize is that a freshly made amorphous material has the most degree of randomness possible. As we leave that amorphous material, some of the molecules are going to move, and as they move, they're going to do so in such a way as to lose energy. No material spontaneously gains energy from its surroundings. So if materials move with time, they're always going to lose energy. Since the y-axis on this graph represents energy, as the material starts to move with time, it will lose energy and so it will go down. That's represented by the arrow number 1 on this graph. What that means is I make an amorphous material, and when it's fresh, it's the most energetically unstable it can be, and as I leave it with time, the molecules start to move and the material becomes less energetic. That process has a special name and it's called relaxation. The material is said to relax with time. Relaxing really means that the molecules are starting to orient themselves, and I think you can imagine that if the arrow on this graph went all the way down, it would represent the material crystallizing from the amorphous state, and indeed that is often what happens. Another thing you might say to me looking at this graph is, well, hang on, if the material relaxed enough, wouldn't it get down to the extrapolated line, which is where the supercooled liquid would have got to? And again, the answer is yes. What will happen is the material will start to lose energy, and if it loses enough energy that it crosses that dotted line, it will effectively go back to being a supercooled liquid, and that will accelerate its crystallization. This is a really important concept because what it says is you can make a material amorphous, but if you go back and look at it a week or 2 weeks or a month later, it will behave differently. and it will behave differently because it's losing energy. And we need to understand how fast or slowly that material is changing in order to understand its properties. One way we can do that is with differential scanning calorimetry. Now, we haven't talked about that technique yet, but we are going to talk about it later in the term. And the arrows on this graph with the number 2 relate to what happens to amorphous materials when they're studied by DSC. So for now we're not going to talk about it, but I want you to refer to this graph when you do consider using DSC for characterizing amorphous materials. What I want you to see is that the temperature at which we anneal an amorphous material is really important. The closer we store an amorphous material to its glass transition temperature, the smaller the gap between the solid line and the extrapolated line. What that means is, when we hold an amorphous material close to its glass transition temperature, it doesn't have to lose much energy before it hits the supercooled liquid line. When it does that, its crystallization should be a lot more rapid. That would mean that the nearer we hold the glass to its glass transition temperature, the less stable it's going to be on storage, because the more likely it is it's going to crystallize. There is a rule of thumb within the pharmaceutical industry that in order to get good stability of an amorphous material, it should be stored at least 50 degrees or more below its glass transition temperature. And this is the reason why. 50 degrees below the glass transition temperature should increase the gap between the dotted line and the solid line sufficiently that the material never reaches it on storage. Relaxation is therefore a really important process. We have to understand it because all amorphous materials are going to relax with time. And as a material relaxes, its properties are going to change. It's important to recognise that temperature is an important factor in relaxation. The higher the temperature, the faster the material is going to relax. And that's one reason why amorphous materials are often refrigerated. But there's another important factor to consider. If there are other molecules that can penetrate the amorphous structure, that can cause relaxation to occur faster. A really good molecule for penetrating amorphous structures is water. It's generally smaller than the drug molecules themselves, and so water can penetrate an amorphous material. As it does that, it's effectively wetting or dissolving that material, and that helps the molecules to move faster. As a consequence, the more water which is absorbed by an amorphous material, the faster the rate of relaxation. And those molecules have a special name. They're called plasticizers. Sometimes we add plasticizers, especially to polymers, to make them more bendy. And the reason it does that is because those small molecules are getting between the polymer chains and stopping them sticking together. In this instance, water is acting as a plasticizer, and it's helping our drug molecules to move, and that makes relaxation faster. It's one of the reasons why if you have an amorphous material and it gets wet, its properties will change very rapidly. If we think about the candy floss that we talked about right at the start of this lecture, the reason you don't store candy floss in a cupboard for a long time is because it will absorb water from its surroundings, and that will cause it to crystallize. What does this mean for whether we should or shouldn't use amorphous materials in product development? Firstly, amorphous materials have some key advantages. The main one, as I've mentioned several times, is that amorphous materials dissolve much more quickly. When molecules dissolve much more quickly, they will often reach a higher concentration than they would if they were crystalline. What this means is an amorphous material often has a higher solubility than its crystalline counterpart. On the screen in front of you, there are some dissolution graphs for crystalline and amorphous versions of the same drug. Crystalline on the left, amorphous on the right. For now, ignore the fact that there are multiple graphs at different temperatures and just pick the 37-degree data. You can see that for the crystalline material, the solubility is very low, somewhere about 2 micrograms per mil. But at the same temperature, for the amorphous material, there is a much higher concentration reached, roughly around 27-28 micrograms per mil. So in other words, a 10-fold increase in solubility just because the material is dissolving faster. There are 2 additional things you might notice from these data. Looking first at the amorphous material, you can see a rapid increase in concentration followed by a decrease. What's going on? Remember from the solubility lecture, solubility is an equilibrium between dissolved solute and undissolved solid. In this instance, all the amorphous material dissolves. The concentration gets very high, but there's no excess solid left behind. Therefore, the system can be considered supersaturated with respect to the stable state, and after a period of time, the material starts to precipitate, which is why the concentration starts to decrease. The other thing you might notice, and it's relatively unusual, is that the concentration is highest when the temperature is the lowest. And that's a reflection of the enthalpy of solution of this material. It's a very unusual system. There are some disadvantages to amorphous materials, and the main one is stability. Because the molecules are able to move, if they are able to degrade, movement leads to faster degradation. And in addition, amorphous materials often absorb water, so if your material is susceptible to hydrolysis, it will degrade faster. So again, on the screen you can see the rates of degradation of crystalline and amorphous material. At the top is the crystalline material, and you can see that the temperature, which is quite high, 40, 60 and 80, never leads to more than, say, 12 to 15% degradation over 60 days. If you look at the bottom graph, which shows you the same amorphous material, you can see that at the highest temperature, 80 degrees, the amount of drug remaining after 30 days is around about 10%. So 90% of the drug has degraded within a month. Not good for a product, obviously. Having said that, we do still need to consider the formulation of amorphous materials. On the screen in front of you are some reasons why that's important. The first one, which we've talked about already, is that as the molecular weight of compounds gets bigger, those materials cannot crystallise, and therefore they have to be formulated in an amorphous form. But there's some other reasons on here that you might not have thought about. One is that a good formulation strategy is to link the active to a polymer. One reason for doing this is because when that compound gets into the blood, the polymer keeps the compound circulating in the blood longer because the body doesn't recognise it as something to excrete. And that's a principle of the company Polytherics, which was founded by Steve Bracchini from the school. It's not called Polytherit anymore, it's called Absina. Another one is the use of polymeric excipients, so we're going to look at that in a moment. So the majority of your formulation is actually made of a polymer, and so that can't crystallise. Another reason is where you've got a BCS class 2 compound, so that's something with low solubility but good permeability. We might want to make it amorphous to get it into solution and hence to be absorbed. And then we may have a need for some formulation issues. One is where we've got, say, an oral fast dissolving film. The material has to be amorphous to get it to dissolve quickly. And another one is where the compound is needed for injection, but the compound itself is unstable in solution. So in that instance, we have no option but to formulate in a solid form, an amorphous solid form, so that it can be redispersed prior to administration. What that means is we choose to formulate in an amorphous form when the active itself or the excipient can't be crystallized, so we have no option but to formulate in an amorphous form. We need an increased dissolution rate to confer a solubility advantage, so that's like we saw on the slide a few slides ago, to get a rapid increase in concentration, or if the active is too unstable to be formulated in solution but it is needed in a solution state, we make it as an amorphous form so it dissolves rapidly upon reconstitution. So on the screen in front of you are 3 formulation types where amorphous content is absolutely key to performance, and we'll look at them in some detail. The 3 formulation types are solid amorphous dispersions, lyophilized powders, and oral fast dissolving films and tablets. Looking at solid amorphous dispersions first, these are cases where your active is dispersed in a water-soluble polymer. The reason you disperse the active in the polymer is because the polymer itself is the particle which is ingested, and it should dissolve rapidly in water because it's a water-soluble polymer. What that means is the drug, which is insoluble, is rapidly dispersed in water because it's contained either as molecules or particles in the polymer itself. Now, there's a lecture on solid amorphous dispersions coming up later on, so we won't focus too much on the detail right now. But one thing I wanted to make clear is the way to think about these systems is that the drug itself is a solute and the polymer is like a solvent. So if we had the drug and we dispersed it in water and it was molecularly dispersed, you'd have a solution. So in this instance, one of these examples on the screen, the drug is molecularly dispersed in the polymer. because the polymer is a solid, not water, we call it a solid solution. But the way to think about it is the same. The other example on the screen, you have drug particles dispersed in the polymer. If you had drug particles dispersed in water, you'd have a suspension. So because the polymer is a solid, we call this a solid suspension. So for now, it's really important to recognise that there are two types of solid amorphous dispersion: solid solutions and solid suspensions. We can characterise these in terms of components and phases. In both cases on my screen, there are two components. One component is the drug and one component is the polymer. It's the phases that are really important. A phase is where you've got lots of molecules of the same come together. So when we have a solid suspension, we have two phases. One phase is the polymer and the other phase are the drug particles. And those drug particles can be either amorphous or crystalline. When we have a solid solution, however, although we have two components, we only have one phase. The reason for that is because the drug molecules themselves are never aligned up in one phase, and so there is no drug phase. The drug molecules are dispersed in the polymer, and so we only have one phase. This becomes really important when we analyse these materials by calorimetry, which we're going to look at later in the term, because a calorimeter measures phase changes, and a solid suspension has two phases, a solid solution has one phase. A good example of a marketed product which is a solid amorphous dispersion is Sporanox. Sporanox is a formulation of itraconazole, and itraconazole has very poor aqueous solubility. On the plus side, you only need a very small amount of itraconazole to get a therapeutic effect. So when you buy Sporanox as a product, it looks like on the screen in front of you. It's a blue and pink capsule filled with granules. Those granules are very complex. They have a sugar core onto which is sprayed an ethanolic solution of drug in polymer. It's ethanolic because itraconazole does not dissolve in water. So a solvent is used to get a suitable solubility, and then that system is sprayed onto the sugar core. The ethanol evaporates, leaving behind a polymer film with drug molecules dispersed within it. So you have a solid dispersion on the surface of your sugar core. And those are the granules that are in that product. When the patient takes this product, the capsule opens, the granules are released, and because it's a solid dispersion at the surface, the polymer disperses very quickly and the drug is released into solution. And you only need a small amount of that to be absorbed to get a clinical effect. Oral fast-dissolving tablets are a relatively new phenomenon. I mentioned them in the introduction because they're marketed directly to consumers as something that you need without taking a bottle of water with you. So a good example is shown on the screen. It's a tablet for hay fever. So imagine you're in the middle of a field with freshly cut grass, and that starts your hay fever, and you're miles away from a shop to get a bottle of water. These tablets are very good because you can keep them in your pocket and you can just put one in your mouth and it will instantly dissolve because it doesn't need any water. And the reason it doesn't need water is because the tablet itself is amorphous. We looked at some of these in the introduction lecture a few weeks ago, but my favourite example is Neurofen Meltlets. Neurofen Meltlets are a mixture of ibuprofen, sugar, mannitol in this case, and glycine as a collapse protectant. So you mix those three components together in water, you pour that mixture into a blister pack, and then you freeze dry the blister pack directly. And what you're left behind with is a very porous tablet shaped material. Porous like we saw in those SEM images a few weeks ago. So what will happen is you take one of those from the packet, you put it on your tongue, it instantly disperses. The sugar is there to help the material stay solid after freeze drying, and it also helps taste mask the bitter taste of the ibuprofen. The final example are lyophilized powders. Remember that lyophilized means freeze dried. It's just another way of saying freeze dried. So these are solutions that are intended for injection, but they can't be formulated as solutions because the drug is unstable in water. So a good example would be a penicillin. A penicillin will hydrolyze with water. So you can't make a penicillin solution and put it into a glass vial because within a few days all the penicillin will have hydrolyzed. So your strategy in this case is to take the penicillin, you freeze dry it to make an amorphous powder, and you supply that with a solution for reconstitution. That reconstitution solution is isotonic with blood. That means it has the same ionic strength and pH as blood. So when it's injected, you don't get localized pain. So the nurse is going to administer this product, is going to take that reconstitution solution, draw it up into a syringe, add it to the penicillin, which is freeze-dried. Instantly, the penicillin needs to dissolve, and it needs to dissolve without any suspended particles. And the reason it does that is because it's freeze-dried, it's amorphous, has a very high surface area. And that is it. That's everything we need to know about amorphous materials. So take a time just to go through some of the online quizzes that we've set on Moodle. Have a think about in your mind what an amorphous material is for you. There's no right or wrong definition, so come up with a definition that you're happy with. My favourite definition is it's a high viscosity liquid. That means that the molecules have the same structural orientation as if they were in a liquid, but the viscosity is so high the material is not really moving. Think about the glass transition temperature. The glass transition temperature is really important. If you want to keep an amorphous material stable over time, it needs to be stored below its glass transition temperature. Remember that amorphous materials can be formed with different processes, and that formation might be intentional or unintentional. If you want to make the material amorphous, you can spray dry it, you can freeze dry it, or you can quench cool it. But remember that if you use any other type of mechanical processing, such as tablet compaction, there's always the chance the material can become partially amorphous. Remember also that even though it may be a small amount of amorphous content, if it's located at the surface of the powder, it can have a disproportionate effect on how that powder behaves. None more so than in dry powder inhaler formulations, which we'll look at in a separate lecture. The last thing to remember is that amorphous materials have a number of key properties that make them very desirable when we're trying to formulate difficult molecules. The first and most obvious is that the dissolution rate is usually higher. A fast dissolution rate usually leads to an increase in solubility, and an increase in solubility usually translates as better bioavailability. Remember also that amorphous materials have some undesirable qualities, usually stability. And that stability can mean either chemical or physical. In terms of chemical stability, your molecule might not be there after storage if it has chemically degraded. In terms of physical stability, if the way that your product works is dependent upon there being amorphous material, and the amorphous material crystallizes on storage, then your product won't work if it becomes crystalline.